Good day everyone, I am Dr. Josh Aragon and I'll discuss translating a statement into a compound proposition. Translate the sentence into a compound proposition using propositional variables and connectives. If Mr. De La Cruz told the truth and Mr. Santos did not hear anything, then it cannot be that the butler did it and that the butler returned to his hotel room that night. First, let's assign propositional variables to each statement. Our first propositional statement is the sentence, Mr. De La Cruz told the truth. Hence, let P represent the statement, Mr. De La Cruz told the truth. Our second propositional statement is the sentence, Mr. Santos did not hear anything. As you may notice, the word not may signify the use of negation. However, we will disregard this as removing the not in the propositional statement would make it grammatically incorrect. Therefore, let Q represent the statement, Mr. Santos did not hear anything. Our third propositional statement is the sentence, the butler did it. Hence, let R represent the statement, the butler did it. Our fourth and probably the last propositional statement is the sentence, the butler returned to his hotel room that night. Thus, let S represent the statement, the butler returned to his hotel room that night. Now let's look for the propositional connectives we can use. Reading the whole sentence makes us think that there is an implication because of the use of if and then. Below is a symbol that serves as the propositional connective that indicates implication. An implication claims that a given proposition, called the hypothesis or the antecedent, entails another proposition, called the conclusion or the consequent. Let us look for the antecedent in this statement. Let me give you a hint. The antecedent in an implication is always after the word if and comes before the word then. Hence, our antecedent will be Mr. De La Cruz told the truth and Mr. Santos did not hear anything. The antecedent here uses the word and that connects our two propositional statements, P and Q. Thus, there will be a propositional connective between P and Q. And the symbol for conjunction shown below is used. Now let us look for the consequent. While the antecedent comes after if, the consequent can be read after then. Hence, our consequent will be, it cannot be that the butler did it and that the butler returned to his hotel room that night. We may notice that there is too much going on in the consequent. As we extract the parts, we may observe the conjunction used as the word and connects our two propositional statements, R and S, as well as the negation used that corresponds to the two propositional statements. Therefore, we have the compound proposition if P and Q, then the negation of R and S. Or we may say it like P and Q implies not R and S. Our next topic will use truth values to determine the form used in a compound proposition. Here's another implication for you. By using truth tables, determine the form of the compound proposition, the negation of P and Q implies Q. There are three forms of compound propositions, namely tautology, a compound proposition that is always true no matter what truth values are assigned to the propositions; contradiction, a compound proposition that is always false, which is the absolute opposite of the tautology; and contingency, a compound proposition that can be true or false, hence making it neither a tautology nor a contingency. Now that we know the forms of compound propositions, we can look for the propositional variables used to know how many vertical columns we should use. Remember that the number of columns of your propositional compound will depend on the number of propositional variables used with the formula 2 raised to n plus 1. Since there are only two truth values, T or true and F or false, 2 raised to n is used, wherein n is the number of propositional variables used. In this case, the number of columns would be 2 raised to 2 plus 1, which gives us 4 plus 1. One column is added as this column serves as the cells containing propositional variables and compounds we will extract later. Hence, the number of columns required for this compound proposition is 5. 2 rows can already be made by getting the variables out of the given compound. Now, let us pull each compound we can make of this implication. We can get P and Q. The negation of P and Q. And lastly, the negation of P and Q implies Q. We always start our truth table on the first row, P, by placing the truth value T on half of the columns and the truth value F on the other half of the truth table. Then, under the row Q, place the truth values T and F in alternates. Now we can identify the truth values of other rows. Conjunction takes place in the third row. Note that conjunctions will be true only if the truth values of the propositions are both true. Hence, only the first column will be true and the rest will be false. Under the fourth row is just the negation of the third row. Negation turns the truth value of the original proposition to its opposite, or simply, true becomes false and false becomes true. Hence, only the first column will be false, and the rest will be true. The fifth row involves the implication of the fourth row as the antecedent and the second as the consequent. Also note that implications will be false only if the antecedent is true and the consequent is false. Since the fourth row serves as the antecedent and the second row serves as the consequent, we'll be looking at the truth values from right to left, or simply backward. Thus, the second and fourth row has the root value F, while first and third row has the truth value T. Looking at the truth values of the fifth row, there is a mix of true and false. Therefore, the given compound proposition is not a tautology, not a contradiction, but a contingency. Now that we've familiarized ourselves with truth tables, let's investigate one of the logical equivalences and what makes a compound logically equivalent. Use truth values to verify this logical equivalence, not P and Q, if and only if, not P or not Q. Components we can get in this compound proposition are P, Q, not P, not Q, P and Q, not P and Q, and lastly, not P or not Q. Keep watching until the end of the video to know why I did not include the whole proposition. Once again, set half of the columns of the first row with the truth value T, and the other half with the truth value of F. For the third and fourth rows, we know that in negation, true turns false and vice versa. Looking at the fifth row, it's already discussed earlier that conjunction will be true only if both propositions are true. Hence, only the first column will be true. For the sixth row, negation occurs again towards the fifth row. Hence, these true values. There is a disjunction for the last row between the negation of P in the third row and the negation of Q in the fourth. Disjunction is false only if both propositions are false. Hence, considering the truth values in the third and fourth rows, only the first column is false. As you may notice, the truth value of the sixth and seventh rows, which are the component propositions of the logical equivalence, are the same. Some may have already noticed that we use the biconditional in forming logical equivalences. Biconditional is only true if both propositions have the same truth value, or simply a true-true and a false-false statement. And that's what we observe in this truth table. Hence, we can conclude that logical equivalence is a biconditional in a tautology form. This compound proposition exemplifies logical equivalence, particularly De Morgan's law.